Right now we're going to be looking at a molecular geometry activity. In fact, they're already involved in it, and I'm just kind of getting caught up on this video. But what they've done is we looked at our homework 7A, and based on that, and based really just on our Lewis dot diagrams, they're going to look at these two values. They're going to think about the number of areas of electron density and the number of areas of lone pairs on the central atom. And also in front of them, they have this chart. And they're filling that information in right here. So again, these are the two main things that I tend to look at. The other one, this area of bonds, number of areas of bonds on that central atom, it just kind of goes along and it always ends up working out if you look at the other two. So we're trying to figure out our number of areas of electron density on the central atom. That's huge to know that part. And also the number of areas of lone pairs on that central atom. So to give an example, if we had something like ammonia, where we have our 3 hydrogens, and we have a lone pair on that central atom, we would look at that and say, yeah, we've got 4 areas of electron density on that central atom, 1, 2, 3, and 4. And out of those 4 areas of electron density, we've got 1 lone pair. So in looking at that, could easily come along and say 4 areas of electron density with 1 being a lone pair, that would have to be trigonal pyramidal. And so what they're doing is that they're coming in and they're just very tiny. They are drawing their their Lewis dot structures. Another example for us, what if we had something like the carbonate polyatomic ion? So in this example, and I'm just going to avoid putting my brackets and my charge right now, but that's what it looks like. As far as our areas of electron density, what I want you to see from this is you've got 1, 2, 3. That double bond counts as 1 area of electron density on that central atom. So you've got 3 areas of electron density on the central atom with 0 lone pairs, and looks like we got this guy right here, trigonal planar. So the unfortunate thing is a lot of this video, a lot of today's lesson is going to be with manipulating little tinker toys. We're going to be playing with some little model kits, and that's not going to be represented very easily on the video. So it might seem a little bit not as understandable as if you were in class. But I'm going to let them get caught up, and then we are going to continue. Okay, so now what we're going to do, we've got all those examples drawn into our chart, and we're going to think about what our different terms mean for these shapes. We've got both electronic and molecular geometry. I'm really not a big fan of the way I have these phrased here. The way I really want us to think about it, let me talk about VSEPR first, and then we'll look at those different shapes. So VSEPR, and everybody should write this down at the top of your chart, there's a little place that says VSEPR, and what that stands for is valence shell electron pair repulsion theory. It's a mouthful, easier to say VSEPR. Valence shell electron pair repulsion theory. So just like it sounds, you've got electrons in your outer energy level, your valence electrons, and they pair up and they're attached in different areas on that molecule, and they tend to repel one another. And because they repel one another, that molecule takes on different shapes, and it has different bond angles. So just like we read right here, it says, since pairs of electrons in bonds with other atoms are negatively charged, they will try and push themselves as far apart from each other as possible. This helps to describe why molecules take on the shapes and the bond angles that they do. And I don't know if any of you guys have cats, but I know I've seen this type of arrangement before, where cats tend to do the same thing. They repel each other, they push away as much as they can from each other. But going back to our real science that we have here, we're going to look at how this electron repulsion affects our bond angles. And we will also, in the process, we're going to build these shapes with these little molecular kits. And again, you're going to be missing out at home if you're watching this because you're not going to see what these look like. But eventually I'll show you a video that you can watch that might be helpful. But we're going to look at both the bond angles and why these shapes are named the way they are. Because guess what? You get to know this entire chart. You need to know the whole thing. You need to be able to name all of these. So if you can look at it and make sense out of it instead of it just being pure memory, then that sure helps. All right, the first one, and everybody in their seats has a little molecular kit, except for this first one. You guys do not have this. So the first one is just a situation where you have two areas of electron density. So I have one in my hands that has two little nubs on it, and I'm putting the straws on there. That is representing those two atoms. Hopefully you can see, as my fingers are holding this out here in front of you, you can see why this is named the way it is. So the name of it is linear. Now in this case, it has both the same electronic and molecular name. You'll notice that the molecular structure is really just a subset of the electronic structure. There are 5 main electronic structures, and as we go through here, we're going to see that linear is one. So I'm going to look at every single case where I have 0 lone pairs. One electronic structure is linear. Another electronic structure is trigonal planar. Another electronic structure is tetrahedral. Another electronic structure is trigonal bipyramidal. And our last electronic structure is octahedral. Now, those are 5 main groups. Those are our family. Those are our family structures or electronic structures. The molecular structure, if there are no lone pairs, the molecular structure is named exactly the same as the electronic structure. But if there are lone pairs, then it takes on a different name because of those lone pairs of electrons repelling and pushing away those other atoms or lone pairs. So in linear, again, I'm holding this up to the class here. What do you think that bond angle is from one finger to the next, from one atom to the next? What angle do you think that takes on? 180. So what they're looking at is I have something with this in the middle and then like this, and we can see that that angle right there is going to be 180 degrees. So now the next one, for trigonal planar, I am going to find one of my little central nubs that has 3 little pegs on it. So this is what I'm choosing, and everybody sitting at your desk, you should be grabbing this guy also. So grabbing this and putting the straws on, because our first example, we see that we have 3 areas of electron density and 0 lone pairs. Hopefully you're understanding this, that when I remove a straw and there's just a little nub there, that's a lone pair. So my example right here, there are no lone pairs. So in this case, wow, that sure looks like a triangle to me. So I've got this triangle, and it is in one plane. It is flat. So that's how you can remember this. It's just a triangle that's flat in one plane. So that's going to be trigonal planar. If you had to figure out your bond angle between those two atoms, think about a circle is 360. So what's your bond angle right there? 120. And these are degrees. All right, still with our 3 areas of electron density. So I've still got the electronic structure of trigonal planar. But what's going to happen is one of those atoms goes away, and now I have a lone pair right there instead. So this lone pair that I am holding on to means that my molecule is now bent. That's what it looks like. It's a bent molecule. Because this lone pair that I'm holding on to is so repulsive, it is pushing these 2 atoms even further away from that lone pair. So now instead of saying that it's 120, all we have to know is that it is less than 120. You don't have to know exact amounts, but it's less than 120. And that's really about all we can do with this guy. Otherwise, that's the only type of shapes we'd have with our trigonal planar electronic structures. Okay, next one. In this next one, we have 4 areas of electron density, so you should be grabbing that little molecular structure. And it should look like this. Again, you're putting all the straws on there. So put all those straws on there. You've got 4 straws, 4 little nubs that you put those straws on. What does tetra prefix mean? 4. So you've got these 4 nubs, plus if I were to put my hand against each of these like this, I'd see that there are 4 possible faces. If this made a 3-dimensional structure, there are 4 faces to that. So this is a tetrahedron, or it's tetrahedral in shape. Okay, so that's our first one. And that's when there's 4 areas of electron density, no lone pairs. The molecular structure is tetrahedral. Now, this is the only one that really you have to just purely memorize, unless, and I keep meaning to do this, go and talk to a geometry teacher and asking them to write me a proof for this, because I don't know where this number comes from. But the bond angle between this is 109.5. Every single atom, it's all the same. Hopefully you can turn that around and see it would always be the same in every single case. And that number is 109.5 degrees. All right. So now, still with 4 areas of electron density, but one of those areas now being a lone pair, what we see is, hey, that looks like a triangle again, right? Just like we had earlier. But think about how my fingers are pulling this up. It's pulling up into a pyramid. So it is trigonal pyramidal is what we have here. Trigonal pyramidal. And when we look at our bond angles on this, remember it was 109.5, but this lone pair of electrons that I'm holding on to is really repelling these atoms, so I'm pulling them away. I'm trying to pull them away from that lone pair of electrons, meaning it's no longer 109.5. All we have to say is that it's less than 109.5. Less than 109.5. All right, now we've still got our 4 areas of electron density. I'm going to pull away one more, and it doesn't matter where it comes from. It's all going to end up looking the same. So now again, I see I've got another structure that just looks bent. So there's our bent molecule. Notice that this bent molecule has a different electronic structure than our previous bent molecule. So there's 2 bent molecules, but they have different electronic structures. All right, notice our example in this one. Our example is water, because water is definitely very polar, where you have these 2 areas where you have the lone pairs. So these 2 lone pairs of electrons are really repelling these 2 atoms. You get this very bent molecule, get a much greater share of the electrons on this side that I'm holding right now, much lesser share on this side. Again, using our mentality of lone pairs pushing away those other atoms or electrons, what we're going to say here, I always love this, it's less than 109.5. So as far as exact numbers, we're not worried about those. The less than 109.5 is typically somewhere around 107, somewhere around there. And then the less than is usually 103, 104, something like that. But we're just going to use the terms less than and then less than. All right, that's it for our first 3 electronic structures. Then we move on to the next ones. And you guys hopefully would ask questions if you were confused. The next one we look at, we've got 5 areas of electron density. So I'm pulling out this structure right here that I can put 5 straws on. So 5 areas of electron density, no lone pairs. Now, as you play with this in your hand, right now I am holding on to the axial part, the axis, as opposed to in the middle, here I can turn around these 3 atoms. This is the equatorial portion. I'm not so sure I'm going to be able to draw this, but let me try. Here, if we have our hub here, the axis does this, goes straight down, and then the equator is coming out from here like that. So that's what we're looking at. The blue is the axis. That's what my fingers are on right now. And then the equator, I've got those three that I can kind of spin around. So now with this as far as the shape goes, when I hold it, I'm going to tilt it just 90 degrees. When I tilt it, do you guys see a triangle? Right? I've got a triangle that is pulled up into a pyramid. So a triangle that's in a pyramid, that's what I've got on this side. If I flip it around, again, I've got another triangle that's pulled up into a pyramid. So it is trigonal bipyramidal. Stare at it, play with it, make sure you understand why it is named that way, because to just merely memorize, for me, is really challenging. But if I can kind of visualize something and think about why it has that name to the shape, then it makes it so much easier for me, and that's what you guys are going to have to do on this test. So this one is trigonal bipyramidal. Again, that's no lone pairs. Now, when we start removing pairs, or removing atoms and getting lone pairs of electrons, I'm sure this is going to be a little bit of a challenge for you to fit on here, but let's try it. That these lone pairs that we add on are going to come from the equator. So we're looking at our trigonal bipyramidal electronic structure. When we start removing atoms and getting lone pairs, it's going to come from the equator. So again, I'm holding my axis. I'm going to remove one of them from the equator. So mine looks like that. And this one always makes me giggle a little bit because I always imagine these chemists sitting around a table in a room for hours and hours on end trying to name these things, and they just got a little loopy. And so this one they named seesaw because it goes back and forth like this. So we're making it look like a seesaw. This is our seesaw shape. Now, if we think about our bond angles, oh, I never did bond angles on the last one. Okay, so I'm going to put my straw back on for a second. Notice that since we have our axis and our equator, we really have two different bond angles that we can talk about. Again, my fingers are holding on to the axis. I'm holding on right here. And as I hold on there, I can look at the angle between the top, my top finger, and one of these guys on the equator. That is 90 degrees. I'm going to call that my axial bond angle. So 90 degrees right here is my 90 degrees. Okay, so that's going to get plugged in right here. So for my equatorial, when you guys look at the atoms on the equator, what's the bond angle there? 120. Okay, and now we remove one of those and we got that seesaw shape. And remember what happens with that lone pair of electrons. Now, all of those guys, we don't have a 120 anymore because I removed that possibility. I take that back, we do. We've got it right here. So all of those guys squish just a little further away from that lone pair of electrons. So what that means is this is going to be less than 90. This is going to be less than 120. Okay, another one of those atoms comes off, and it comes off from that equator. So now in this case, what does that look like? That's a T. So we have a T shape. And in that T shape, we've got these two lone pairs are really repelling the atoms, everything else. So because you've got those two lone pairs, these are no longer going to be 90. In fact, they're not even less than 90. We're going to say it is less than 90. And there are no, you've only got one atom on the equator. So because of that, there is no equatorial angle. All right, last one comes off of that equator. So again, this should look fairly familiar. That just looks like a line. So all I'm seeing are what I have in blue right here. I'm just seeing this line. And we know that our bond angle in this case, again, is going to be 180. There are three lone pairs around it, but they're affecting everything equally. So that's why it looks like that. Okay, now we move on to our last one, and this is going to be the one that has 6 areas of electron density. And for this, I can hold it like this. This is what your model should look like. I can hold it like this. I can hold it like this. It doesn't matter where I put my fingers. It all looks the same. So there is no equator and there is no axis. It is all identical. And hopefully you guys are playing around with this and convincing yourself of that as well. So when I look at, let's go about naming this. First of all, I've got 6 areas of electron density, but we're calling it an octahedron. Why would we do that? 8 faces. So if you were to think about the faces that are created here, there are 4 on this side, then 4 on this side. So that's the octahedral shape that you have. So bond angles, every single bond angle is identical. What do you want to call that bond angle? 90 degrees. There is no difference between axial and equatorial. So when one of these gets pulled off, just doesn't matter. Just take one off. So now, in this case, I see that I've got a, and I guess I should do this for people at home, that what this is you've got, here's your central, you've got that, you've got this, and then, how can I do this? I'm not very, I guess this is also on that. That's a little hard to see, but it's kind of like a jack. If you ever played jacks, I don't think anybody plays jacks anymore, but that's what it looks like. And so all we're doing is removing one of those. Now, when you remove one, right now I'm holding on to a lone pair. When you guys look at that, what's the shape that you see? That's a square. But notice that it's pulled up into a pyramid. So that's where the square pyramidal comes in. It's a square pyramidal shape. And when we start looking at the bond angles, it was 90, but I'm holding on to that lone pair of electrons, which is repelling all of these guys. So what do we want to call it? Less than 90. Less than 90. And then our last one that we're going to pull off, it actually does matter, and hopefully you guys can figure this out, that remember these electrons are repelling each other. So there's going to be equal repulsion. In order to make it equal, I need to grab the opposite side. So in this case, again, I have a square, but now that square is all in a plane. It's all flat. So I've got a square planar shape, which is what we see right here. And because I have my lone pair of electrons on each side, they are repelling equally. So what do you think you say about your bond angle again? 90. It's just 90. Okay, awesome. So hopefully at home you can figure out, maybe Google some things if you need to. I'm going to keep moving on. Now what we want to do is we want to think about something about the polarity of this molecule. So here's our little cartoon. Help, help, I'm dissolving. But bears are insoluble. Well, that's easy for you to say. You are not polar. So polar substances dissolve in water is what we're going to end up seeing. So polar molecules versus nonpolar molecules. What we're going to see is that, and we've seen this already, that depending upon how those electrons and atoms are distributed in a molecule, you can have positive and negative sides to that molecule. Water, we know, is very polar. So when we figure this out, we end up seeing that a polar molecule dissolves in another polar substance, and a nonpolar molecule dissolves in a nonpolar substance. This is what you need to write on your paper. In fact, you should probably be flipping to the back off the chart now, and flip to the back for a minute, because there's some this information is really listed on the back side. Like dissolves like. Polar dissolves in polar, non-polar dissolves in non-polar. Pretty important concept that you guys should walk away from chemistry with. So I'm not sure that I have this on your notes, but I would write this in. This we've looked at already. I just wrote this here to remind you guys. If we wanted to know something about bond polarity, do you remember what we looked at? Okay, it was electronegativity differences. We looked at the differences in electronegativity and we could figure out what that polarity was for that bond. But now we're going to look at something known as molecular polarity, not bond polarity. I'm done with bond polarity right now. We want to think about the molecules themselves. And the way to do this is you draw your Lewis dot structure. And if your Lewis dot structure, if you have a central atom with no lone pairs and every single type of atom that's attached to it is exactly the same, well, think about symmetry or a tug of war. No one would win that tug of war. It would all be identical. It's very symmetrical. So no lone pairs and all of the atoms attached to it are the same type, then it is going to be nonpolar. However, if the central atom has no lone pairs, but the atoms that attach to it are different, then that means one of those guys is going to have a greater share of the electrons than the other, so it will be polar. And then also, if you have a situation where you have lone pairs on the central atom, we're going to say that it is polar. Of course, we do have some exceptions. There's always exceptions. And these are our two exceptions that we have. And the easiest way for me to really illustrate this is with my molecules. And I'm going to go ahead. I've got them in front of me, my little kit. But let's go ahead and draw these. I'm just going to do a quick little drawing. It's not going to be complete. So I didn't put all my lone pairs around everything and put my brackets in charge, but that's what this would look like here for your Cl. All right, that's what that one should look like. So if you notice the shapes here, in our ICl2, we've got, and I'm holding up my little molecular kit here, my little Tinker Toys, we can see a situation where we've got a linear molecule with a trigonal bipyramidal parent structure or electronic structure, but it is linear. But because I have these three lone pairs around my central atom, it is very symmetrical. There is no side of this molecule that is more positive or negative than the other side. So even though I have lone pairs around my central atom, this one is considered nonpolar. We'll come back and write this on a chart in just a second. Same with this one, which is my ICl4. In this case, I've got the electronic structure of an octahedral, but it is square planar because I've got these two lone pairs right here, so there is no side of that molecule that is more positive or more negative than the other side. Again, maybe you can just kind of envision it as symmetry. So heading back, let's go back here. I think what we should do now is just go ahead and fill in something about the polarity on all of these. So the first one we're flipping back to our chart. We've got this linear situation with these guys, and we're going to do it with these examples that we have drawn. So for the beryllium hydride, we've got, are you guys going to call that polar or nonpolar? Nonpolar. I look at that and I see no lone pairs on the central atom, and everything around it, surrounding it, is identical, so it's going to be nonpolar. Okay, next one, our carbonate. What do you want to call it, that one? Nonpolar. Okay, then we get to our bent, and I see the lone pairs right there on that central atom, so this one's going to be polar. I get to our methane, CH4. Again, no lone pairs, everything's the same. That's going to be nonpolar. The next one, we have ammonia that has lone pairs on that central atom. Think about how that was pulled up. That triangle was pulled up into a pyramid. You've got a much more negative side to that molecule there, so that one's going to be polar. Water, we know, is very polar, but those two lone pairs that are on that central atom make it very polar. Okay, then we get to our PCl5. What do you want to call that? Nonpolar. Okay, SF4, because of that seesaw shape, you've got that lone pair right there. That makes it polar. Here we've got our BRF3 T-shaped. You've got two lone pairs. That certainly makes it polar. We have the exact same examples we went through, but hopefully you guys can look at this and see this linear one now. Because of where those lone pairs are placed, it is actually going to be, excuse me, it is going to be nonpolar. Then we get to our octahedron. It is also nonpolar. Our square pyramidal, it's a pyramid. It's pulled up into that pyramid because of this lone pair of electrons. That one's definitely polar. And then our last one, the square planar, because of these two lone pairs and their placement, if you look at how you created that molecule, it is actually nonpolar. I think these are just going to take some time for you guys to play with and make sure you really understand those Lewis dots and what the shapes look like compared to it. Okay, last little thing we're going to do, 4 more Lewis dots and identify the polarity, the molecular polarity. I'm not looking at bond polarity, I'm looking at molecular polarity, and I really want to make sure that you understand the difference between those. So when we look at CO2, I'm going to have C, O, and O. I know my needed, available, and shared. I've got 24 for my needed. I've got 12 plus 4 is 16. Gives me 8 for my shared. Looks like I'm going to have 2 bonds. I'm sorry, 2 areas of electron density, but it's going to be 4 bonds. And I throw in my lone pairs as needed. There we go. Now, it doesn't ask us this, but we could certainly classify this molecular structure. What do you want to call that molecular structure? I heard it. Say it louder. Linear. That's linear. Is that polar or nonpolar? Nonpolar. There are no lone pairs on that central atom. It's a linear shape. Okay, next one that we've got H2CO. Which one's going to go in the middle? C, carbon always goes in the middle. Then I'm going to have an oxygen. You know what? I'm going to change that just to make it a little bit prettier. I'm going to have some hydrogens and an oxygen. So when I do my needed, available, and shared, I've got 8, there's 16, 17, 18, 19, 20. My available is going to be 6 plus 4 is 10, 11, 12. That means we're going to have 8 that are shared, which means 4 bonds. 1, 2, 3. Does it matter where I put that 4th one? Yeah, it does. I got to put it on my oxygen. It's the only one that can hold it. So when I throw in my lone pairs, it looks like that. Now in this case, I have no lone pairs on my central atom. So is it nonpolar? No, and the reason being, this guy right here has a much greater share of the electrons than the others. Because those atoms around that central element are different, it is polar. So we see that we've got a polar molecule in this case. Okay, molecular geometry, what's the shape of that guy? Good, good, good. So trigonal planar, it's all in one plane, no lone pairs. BF3, BFF, and you get these lone pairs around this guy, and that's it. Boron can only hold that many, so again, you've got another trigonal planar, but in this case, this one is going to be nonpolar. So trigonal it's not the fact that it's trigonal planar that made this one polar, it's the fact that the elements were different around it. Last one, we've got carbon in the middle, and we've got some hydrogens and a fluorine. So when you look at that, you should very easily say, wow, this guy's hogging those electrons. It is obviously going to be polar. You've got different atoms surrounding that central atom. The shape of this is just going to be tetrahedral. And that, I believe, is it. Again, this just takes practice, and you certainly have that. I've given you plenty. Thanks. Bye.